Hello, welcome to the stream. Thanks for joining me. Honestly, hope most of you are watching the World Cup final if you're into soccer and not here on my stream, but I do appreciate it if you are here. Um, I think, assuming I have the stamina, I did a work trip this past week and it was pretty exhausting. I just got home yesterday, of Saturday. I was supposed to get home Friday night. So I don't know how much I'm up for, but luckily the last few bits of the chapter on functions is pretty mechanical stuff. So I think that we got past the hard part of making allocate registers work across functions, and so I think that we can do pretty well today. We have patch instructions, which is sort of like a people optimization pass. I say that it's actually like it covers up some of the few bits that emerge from the code generation not necessarily being data flow driven. What I mean by that is sometimes you'll have redundant moves. That's a big one. You'll have move from a register to itself, or you'll have move to an intermediate location and then back to the original, or to a different location. You can collapse those two things. When we're working at the assembly level, there are some inefficiencies that come in that some other compilers would automatically detect with some pretty sophisticated techniques and just never generate that code. But we're in the situation where we have a few cases where we generate redundant code, and eliminating them at this point is a really good thing to do. And the last bit, I think, is probably the more interesting bit that we'll try to cover today, which is the prelude and conclusion. Now, in previous chapters, we didn't have user-defined functions. We had standard library functions, or like runtime implemented functions, if you want to call them that. They're not standard library because they're not implemented in our little subset of Racket. They are implemented in C. So you could call read to get an integer off of the console. But so we haven't had to deal with the whole x86 convention of outside of the entry point and exit point of our program. We haven't had to deal with the stack manipulation, but we need to do that here because the runtime will call into our main function, and if we call any other functions, we need to make sure that the stack is properly groomed when we enter and exit functions. So we're going to take care of that. Yeah. So let's get into it. The thing. Let me switch to the code screen, and hopefully this will be visible for you all. If my head ever gets in the way, let me know. I'll move it to a different part of the screen. I kind of like having it in the bottom right, but if that's not good for you, let me know. Okay, so remember here, you can follow along here on GitHub, Sean Cribb's Essentials of Compilation. This is where we're working from. I'm working from the book in PDF form, and last time we finished 7.9.3. So luckily that was a straightforward transformation. The tests were kind of challenging. As we get farther and farther away from the abstract form and into a concrete form that something else will consume, like our assembler, this gets more challenging to make tests for. So let's. I started to say this and then I aborted. What I want to do first is make sure that we have our interactive web thingy, which is not running. Let's get it running. Muster dev start. Okay. So here we are. Let's refresh this business. So what we were doing in this is we were and it's not obvious because of the colors here. I think I can improve upon that later, but yeah, at work this was using Luster UI, and at work I used Oat for a small project. So I think I might want to pull that in at some point. But regardless, so we have the phases here, and I also included tokenize and parse and type check, even though the type check is sort of part of the phases, but they're never shown in the book. In terms of the graph of the steps we go through, and they're explicit about we don't care, like we'll provide you a tokenizer and parser, but we don't care about that. We're not focused on that. There's a lot of literature on that. They wanted to focus on the back end of the compiler, the middle, and the back end. Anyway, so what I want to do here is note that we have allocate registers and patch instructions in here and uncover live. But if I say, plus x1, let's do plus 41, 1. And if I try to compile to that, it doesn't give me any output. But if I go to select instructions, note that we have some output there. So, so why that happens is here's select instructions, and we have commented out uncover live. So I want to update those so we can get, we can get the live before set. Note that that's there in a comment, but it's not. There's nothing in it. So let's fix that. So what I'm going to do is I'm going to take these and we're going to comment this out, and we're going to go and replace all the stuff before it, and let's import uncover live. Okay, so that's the other thing, is that we have, I think build interference is not an interesting pass because it does for this, because it just builds that interference graph. It doesn't add anything to the output, right? Whereas this uncover live, we can see the live before set of every block, which is good. But let's go ahead and see what happens there now that we've enabled that. Let's compile that. Okay, so here they just say RSP is live before. We have basically the same program. Yeah. Let's do one of our more interesting programs just to make sure that this is working. Let's copy it from our editor. That'll be easier to find. Like this test. Here we go. This will be a bit more interesting one. And we'll go down and grab one of the others as well. But let's do this one. Okay, so this does a bunch of allocations and so forth. You'll note that R15 gets in here because that's our root stack pointer into this. And main block 1 is where it jumps to for this final expression here, that innermost expression. And here we're getting the variables that are used for initializing the two vectors. So you've got vector 42 is an inner bit, and this wraps a vector around that, and then yeah. So and we've got the relative, the instruction pointer relative addressing there. This free pointer being a global. Yep. Okay. So this, we can tell that this is working. We've already tested it pretty well, so I'm not concerned about that. Let's run the interpreter just in case. Yeah, we got 42, as expected. Okay, so now we can re-enable allocate registers, which is going to be interesting. So what I'm going to do here is just copy pasta. And we'll get rid of this OK. And then after uncover live, we're going to say allocate registers. Okay, we haven't updated patch instructions yet, so we're not going to bother with that, but let's see what happens with... Oops, not that. Let's see what happens with our register allocation. An interesting test here. All right, allocate registers. Okay, so we got an error there. Let's see what happened. What was the error? Pattern match failed, no pattern matched the value. Translate location, translate instruction. Oh, is this the error we ran into last time? Let's get it to the stuff before. Let's get it to select instructions. Okay. Uncover live still works. Interesting that RSP is not live before, and I think that's because of this tail jump. Allocate registers. Okay, so there we have an error. Let's dig into this. Okay, so allocate registers definition. I wish I actually had source maps correctly working here. I think I have to turn them on. Let me see if I did. Source map's true. Let's see if we're getting source maps in here. We are. Are we? Let's see. eoc.dev.js. There, this. Okay, so this is the minified. So that doesn't have a map. That doesn't have a source map. It's running that. Okay, I wonder if this is just I have an old version of Lustre and I need to upgrade Lustre DevTools specifically. Let's find out. Yeah, Lustre, well, it's not that old. Let's see what we can update. I think there in our dependency tree there was something that was not up to date. Yeah, our standard lib doesn't. Our standard lib doesn't upgrade yet because something is holding it back. Unfortunate. Let's do clean. I want to just Gleam clean first, and then we will run start. And we got to build the whole dang thing again. That's fine. Okay. Let's look at our build directory here. Yeah, we're still not getting a... It's fine. Let's copy that and then refresh the page. I think there's a genuine bug here. Yeah. Okay, so translate location. Let's see if we can make this make sense even without the source map. Okay. So it's here. There's a let assert inside translate location. So this is allocate registers. Let's look at that function, because I think that we might be encountering something that only happens on JavaScript, which would be bad. Let's see. Allocate registers. Translate location. Okay, so the assignments is... Are we just doing this wrong? No, this is a location. Okay. So I think what I want to do here is pause here on the next go round, and the problem is this is going to be called a bunch of times. So when we can get more specific on the watch. Maybe let's break here and see what variable. I'm assuming it's going to be x, or it's going to be temp1, which is the inc function. Right? So if we go one before temp1 or x1, it's going to be one of those two. So let's go here and see what happens. Okay, so the variable's temp1. So we're inside the main function. And let's go back here. This is the LEAQ. Let's look at assignments. Okay, assignments is empty. Okay, let's go back up here. Yeah, it's empty for the main function. This is main that we're working on. I'm curious if we made a quick test for this particular program, what would happen? Sorry, those are standard library functions. Okay. Yeah, let's look. This is going to make more sense if we look at the Gleam source, I think. Okay, so in allocate registers, We're taking each definition and we're allocating registers for each definition. That's exactly what we should be doing. Okay, so here's this bit. We did introduce this LEAQ function, or LEAQ instruction. So I wonder if we just missed something. Why don't I look at the allocate registers test, because I wonder if we just didn't cover this in some way and we can trigger the same thing. No, we actually do cover this. Let's run that. Okay. Yeah, that's fine. And like, let's look at the snapshot for that. It proceeds. Like in the Erlang one, it proceeds. I wonder if we just have a bug on JavaScript only. That would be really curious. Okay. If you're watching, and I'm sorry this is not staying within Windows, so you couldn't see everything on the right. Sorry about that. If you're watching and you have any ideas for me to look into, drop them in the chat. Okay, so we end up calling translate location with B. A is global, B is var5, whatever that is. So that's temp1. So that variable was never assigned. I would like to look at, because we didn't throw it away, maybe if we go allocate registers here. Okay, so we take the conflicts, we color the graph. Right, and so that's giving us an order with which to assign. Let's go to that. This is not changed at all. But I do recall this, when we changed our graph implementation, I do recall this being a little bit tricky. Right, so this is like, okay, so this is a generic unfold. Generating a list. Quasi-generic. So this is returning item and accumulator. I think if I were to make this more generic, I'd swap those because typically the accumulator comes first. But we're using result to say, keep going or stop. Okay, and then our individual step is pick a vertex that has been unassigned. We go in there. We get the node weights. And we say is the assignment. If it's already assigned, then we omit it. If it's not assigned, we take the size of its saturation set so that we can rank them, and we sort by that. And then if their saturation set is equal, then we compare them. By their location. We kind of like arbitrarily rank the location. And then we find the max. So we want the thing with the most saturated, right? And then we take the location out. So that's just picking which one to do next. Okay. So we got okay. So we got somehow a node in the graph, and I think that what I want to do here is I'm interested in the output of the coloring. So we're going to echo that. And here we're going to resume. I still have the program. Okay. So I want to see what comes out of that coloring. And I don't know that it's going to be legible here, but okay. So let's look at the console. Right, so it came out with an empty coloring, which means there must be a bit where we're not building an interference graph correctly. So that indicates to me there's a problem farther back. Let's do that, and let's get rid of this echo. Oops. Sorry, we're going to allocate registers. We did I not? Echo conflicts. it did not output anything here. Is the issue we skipped a step? It could just be, yeah, we skipped a step. I'm a bonehead. The problem is not JavaScript versus Erlang. The problem is I didn't set up my compiler phases correctly. Yeah, okay. So let's get, I was like, why is it not calling that? It's because I didn't put it in the chain. All right, so we're gonna get rid of that. That's the issue there. Dumb issue. But like, it came about because I didn't put the build interference as a phase that you can output, because I was like, oh, you know, it's just you're just building the conflict graph for the subsequent phase. You don't actually need. Okay, now it's fine. Yeah. Boo. Okay. That should actually probably print star RCX, but whatever. Tail jump is a fake instruction anyway, so we're not gonna deal with that. Okay. Right. So let's just revert that. Then it's not part of the diff. Okay. So I'm so used to my console get aliases. I'm like, oh, there's a UI in here. Okay, I don't really need to look at that, but okay, so this is pretty simple. Restore, uncover live, and allocate registers in the UI. Okay. So what we'll do, hopefully, is get patch instructions done, and then we'll restore it here. That'll be really good. Okay, so patch instructions. Let's look at what they say in the book, and then we will get going. Okay, book and editor. Okay, in patch instructions, you should deal with the x86 idiosyncrasy. That's like literally its entire ISA is idiosyncrasies. That the destination argument of LEAQ must be register. Okay. So additionally, you should ensure that the argument of tail jump is RAX, our reserved register, because we trample many other registers before the tail call, as explained in the next section. Right. Okay. So that makes me not happy, but we'll see. Let's look at patch instructions. We're already going to have to deal with the fact that we need to change this to x86 def call queue. Okay, and then we need to do basically what we've done before. Let's rename this, hi Chris, to patch instructions definition. I'm just going to do it like that, x86.definition, and it maps to x86 definition. And we're going to say we're going to rename that to blocks. Input.blocks, and this is going to be definition. Okay, and this will be blocks. They were more consistent. Okay, and then we're going to say pubfun patch instructions, input x86.program, Okay, and this is going to be input.defs. Well, we'll inline it directly. Okay. Easy peasy. Okay, so we're going to have to deal with the fact that there are additional instructions here. So we need to deal with the fact that LEAQ, destination argument LEQ, must be a register. So if we have x86 LEAQ, this, and we have the only other thing it could be is a deref, right? Then what we need to replace it with is x86 LEAQ, and we're just going to use RAX. And then we'll move from RAX into B. So that covers that. So this kind of bugs me. I wish we could feed back into our register allocation phase the fact that the argument of tail jump should be RAX. But we don't have like sophisticated data flow here. It's really simple data flow analysis. So so we're just going to have to patch it. So let's look at not LEAQ, tail jump. So we have tail jump, and let's say we're not converting it to jump here. We need to do that in the prelude and conclusion, because we need to make sure that we deal with popping the stack, because a tail jump is basically a go-to, but like you want, if something called into this function and you did all of the prelude of like, you know, push the things, push the stack, push the base pointer, all of that, we need to undo that so that it's as if you called the function that we're jumping to, right? Even if that's a you're jumping to the same function, you don't want to do that stuff again and still build up stack frames that you can't unroll when you did a tail call, right? That's the essence of the tail call, is that it looks like no additional frames are created. But since we do create additional frames, we've got to adjust for that. Okay. Anyway, that was a long-winded way to say, hello, Renatius. I thought you were going to watch the soccer match. I thought you were going to watch soccer. Okay. Right. So here, what we want to say is if dest does not equal x86 register REX, right? So if it's not, yeah, if it's not REX, then we need to change this into x86 move queue from and the whole reason we're doing this is that like other things will stomp on other registers, so we need to make sure that we capture that into REX, which is, you know, reserved for return values, and so it's safe for this case. Hello, welcome to the stream, Vadim. Nice to see you. First time? Okay. So, yeah, so if this is a stack location, if this is another register, regardless, if it's not REX, then we need to move it into REX. So this is going to make our little program that we were doing a minute ago. Yeah, fine. Where this program, note that the address of the inc function gets put into RCX. And then we tail jump to it. So what we're going to see in this transformation is that we're going to add a little instruction here in the middle where it goes move from RCX into REX and then tail jump to RAX. Okay. Right. Yeah, I know that there's issues there with integers. Okay, I think that covers what we wanted to do. So let's go down to our patch instructions test. This is probably where it's busted. Yeah. And we're going to have to make all those changes that we did before. How many tests do we have in here? Only 4? Okay. Def call queue as x86. Okay, then, you know, all of this is busted. Because we have a series of definitions, not just one program. Okay, so what is this one testing? Let's see. Oh, this is testing. Right, so add queue gets expanded. Right. So you can't. This is about expanding moves. You can't move from one dereference place to another. You have to move through a register. So like one of the arguments in the ISA must be a register. Or an immediate. So like obviously you can move an immediate value, like a static value, into a constant value is probably a better word, constant value into a stack location, but you cannot move from one stack location to another stack location. You've got to move through a register there. That's what this patch does. Let's look at this other one. What are we testing here? Oh, this is register. Chapter 3 is register allocation, so I'm wondering what we're testing here. Okay, so this is getting rid of redundant moves, I'm guessing. What else we got? Another redundant move. We've got to move from a stack location to a stack location. All right, and this one is about comparisons of immediate values. You have to move the immediate value into a register. That's what this is about. These are all like cases in our patch instructions here. Yeah, like this one is easy. If you're moving from A to B and A and B are equal, then just don't do it at all. And this is the one if yeah, and we don't generate REX derefs, so we're fine there. We pretty much only deref the base pointer, which is fine. That's where we're allocating our things to. I've been following your development for a long time. I'm also developing. Oh, that's great, Fadine. I think that's fantastic. I would love to hear about your language that you're developing and what your goals are, because I think that that's something I've always wanted to do. I don't really have right now the strong motivation to develop one. I might. We'll see what happens, but I am very interested in both the design decisions that folks make on the front end, as well as like how it translates. Like I think that this process of going through the book has been really enlightening to me of the different trade-offs you make in the middle of the process, and there's a lot, especially in these last 4 or 5 passes. I guess you can either lump the register allocation passes together, even though there's separate bits, where the decisions made in this are very much like, we know we're targeting x86, and there are various limitations that we need to account for if we are like trying to meet not just the x86 ISA, but also the calling conventions that are expected for POSIX C calling conventions, and like those strongly influence what we do here. For example, this putting using function pointers basically. Yeah, I feel like making a language is one of those huge projects to get to the point and make it useful for writing other programs. Absolutely. Like, and maybe what comes in my future is understanding this stuff is like really enlightening for how I might apply it in other areas. And one of the things I've been wanting to do for a very long time, but I've run into roadblocks, mostly conceptual roadblocks, is I have the Neotoma project. It's a parser generator for Erlang. It generates Erlang code by basically filling in a bunch of string templates, and that's not good. It produces really bad Erlang code, and it's also encumbered by the fact that the code it generates uses, so it's a parser generator, right? You supply how you translate the kind of raw AST into data structures by doing inline code snippets, but the parser that it generates is really inefficient for 2 reasons. One, it uses an ets table for memoization because it's a pack-rat parser, but it also uses monadic parser combinators, and it's better to generate the direct Erlang code than to wrap it up in a bunch of closures. So that's one project I want to get back to, that I feel like this experience of doing a compiler from top to bottom, it's not completely to bottom, and I'm writing an assembler, but that would be really illuminating, and I might be able to apply some of the lessons there. The flip side of this is a very didactic format. The incremental bits, and I don't know that I'll be able to do that with, I won't say huge install base of Neotoma, but like there's some definite backwards compatibility concerns that I ran into quickly, partly because it's self-hosted as well, but I need to like conceptualize and plan that beyond just the, oh well, I want to rewrite it so it's more efficient. I need to like have really targeted goals, and like have especially intermediate ones where I don't have to do the whole thing at once. I have to conceptualize it ahead of time and like break it down, and that's something I need to do probably offline. It might be an interesting stream, but I don't know that it'd be really a great one. But yeah, I thank you, Chris, for that encouragement. I really do want to do that. The sad thing is, like, part of the reason why I feel like this particular project was really successful so far is because of Gleam. Like the and maybe I just do a new Neotoma, which is in Gleam but compiles to Erlang, and say, hey, if you want to use this, you got to use the Erlang generated sources. I'm sorry. Deep work is tough to do on stream. Yeah, I agree. And some of what would make it less interesting is I might be sitting there thinking and not talking. The mechanical updates that we're going to do here are a lot easier to do on stream because they're not interesting, but they're straightforward, and I can talk through them and explain what I'm doing. Okay, so we have done this transformation before. Let's grab one from a nearby test where we did that. Okay, we have the base block. Let's get this main because that's going to be, yeah, we don't need the base program. This is going to be, we'll call it main one. I think that's probably the best way to do it. And I don't remember what I copy pasted. Yeah, so let's just call it main. And this is not the base program, and this is blocks. Okay, and we need to import EOC langs lfun as l. Okay, and this is not a thing where we have okay, we're going to call this main 2 and just do that bit again. Okay, and then we'll wrap this with program. And this is main, and we'll do main 2. Okay, and let's go ahead and make the same transformations down here. And this is, let's rename that to main 2. I'm glad that this is not a hard transformation to make at this phase. I had set up a lot of the same blocks, plural, a lot of the same things in other. I can just copy this from up here. And why don't I just, rather than copying the let main, we'll just copy the bit that changes. Okay, get rid of the base program. Okay, so this is a little bit of a different kind of test. We're not doing straight equality here, but let's do this. And this is blocks. And we've got a problem there. Okay, so let's do what we've done in some of the previous ones, which is match on the return value with the, we'll call it main. And then down here we'll do main.blocks. And what do we have wrong? Why is that not formatting? Okay. And let's look at this one. Are we doing a similar thing there? Yeah, we're kind of asserting the contents of that. So I'm gonna copy this, and then we'll dump that in here. And this is blocks. And then we gotta close that. And then down here we'll do main.blocks. Okay. All right, so that's all the tests. I want to make sure that this this passes first. Okay, 152. We didn't get rid of the base program. We don't need that. Okay. Okay, so those still pass. We need to make a test for the other bits, and I think that I just want to do some snapshot tests, and I think that will be best. So I'm gonna get our all of this, which we copy pasted to every test file. Allocate registers. Okay. And let's get all those imports added. So hopefully we'll get to the prelude and conclusion. I think that's interesting to get done today. I want to cover my bases and have tests for all this. Okay, so those are just complaining that they're not used. And yeah, you're complaining as well. So we want to test we want to test the tail jump and the LEAQ thing. Those are the two things that we added, right? So I think that what we'll do here is we'll use our little program that we had before that is just this, because this returns the value of ink. And we will do, so we've got this, and then we're going to get, let's see what we did over here. Yeah, we're going to do something similar to this. We're going to call okay, we need to import Gleam list, import pprint, and import birdie. And this is going to be patch instruction tail jump test blocks. All right, so let's see what that looks like. I think that what we're going to see, yeah, quit complaining. I think that what we're going to see here is right. So we get the RCX moved to REX before the tail jump. That covers that. The other aspect there in our patch instructions is we need to force it to go to a stack location. When did you create an emulator? Oh, this is Birdie. Yeah. This is Birdie. I'm not emulating anything. Now, there is an interpreter for this, but this is interpreted at the top level language, right? It just goes through the type checking and then it interprets. That's all it does. What about the other window? What other window? This? Yeah, so what this is doing is just giving us some interactivity with the compiler. Yeah, I mean, honestly, it's just I've got one module for the most part that handles all of this, and there's the Lustre UI separate from it, and it's just like take whatever is in this text area, run it through the phases of the compiler, and then pretty print it over into this space. If you click interpret, it does just the top level bit and like outputs the result of the program, which is always an integer. But if you do something like, say, select instructions, you get, in each intermediate form defines how to pretty print itself. So like we could go to explicate control, which is the C-like language, and note here that this is not assembly, and it's not C, but it's kind of like C-ish semantics. But if you go to remove complex operands, you get something else which looks more like racket, and that's just making sure that you don't have anything complicated in an atomic operation. But we can go like, go here, and it does, it does less. So type check is just like, it doesn't do much, but it wraps this function with, hey, it has the type of integer to integer. And then, shrink. What does shrink do? Shrink for this program doesn't do anything interesting. Uniquify is going to turn all of those. So like this is a fun thing to play with. It helps me validate that what I'm trying to do is actually, the transformation is actually working beyond what I can do in the tests. The tests are sort of like, we contrive the scenarios, but to see it in action and go, yeah, that looks like the correct behavior is really good. That's why I built this. So reveal functions just like annotates this with, hey, it has arity 1. Limit functions actually removes the type annotation. That's fun. Expose allocation is about vectors. Uncover get is about mutable variables. Remove complex operands. So that pulls that function out into a temporary variable, and then you do the function application on the temporary variable. That's useful for what this actually does is this turns into the LEAQ instruction, and then we get our transformation into the C-like language. So go from functional to and expression based into imperative. So here we're assigning inc1 to temp1, and then we tail call into it, and then and then select instructions turns it into an assembly-like language with variables. And so forth. And this is all the bits that we do. Uncover live computes the liveness of each variable, and register, and then allocate registers turns these into, so like it uses all that information that's built up before and turns it into actual assignments to registers and stack locations. So going on and on and on here, but if I want to exercise this, I need to get a program that has enough I either need to contrive it, or I need to get a program that has enough to allocate stuff to stack variables, like run out of registers. And I think that it's going to be a little bit hard to do. While we're at it, since we finished patch instructions, let's go ahead and re-enable it in the editor, or in the Explorer, and then we'll do and then let's see. Okay, so we've got, oh, don't want that. Here's our test. I'll accept that birdie snapshot in a minute, but let's do patch instructions. And there. So you can see like our little bit with, and we could see it down here in kind of like the abstract form, but when we print it out to assembly, you can see that, you know, it's looking up link using the instruction pointer relative addressing and putting that in our CX. Here's our argument to the function 41, and then we did this transformation. If we go back and do allocate registers, you can see that that instruction is not in there. But when we do patch instructions, we get RCX moved into REX, and we tail jump off of REX. So, yay! That's good. How can we exercise this particular clause? I'm hesitant to contrive one, but I might need to. The thing is, like, we could also choose to export this and just test that individual instruction, but I kind of don't want to tie my tests too much to the implementation here. I just want to get the output. Let's go ahead and use our other example program. I just want to say map inc test, because that's really what our example from this chapter is. It's not that one. It's this thing. And we'll change the title. I still haven't accepted that snapshot. Okay. Now this is, allocating vectors and things. So it's no, we got assigned registers here, so it didn't test that at all. These are being used for vector manipulation. We're not putting functions into them. I'm curious why this particular... Oh, you know, patch instructions doesn't look at... It looks at individual instructions. It doesn't look at pairs of instructions. So we have no way... Yeah, I thought there was a bit where it would look at windows of 2 instructions and like look at the common thing, but it doesn't do that. We could potentially write another optimization that looks at 2 instruction windows. I don't know that it would be semantic preserving, but yeah. It's also possible that, you know, the processor or the assembler could look at those and go, "What the hell are you doing, man?" I'm just going to move it for, like, do 1. Anyway. Okay. So... The other thing, though, is we would have to special case it, because here's an explicit expansion where, you know, each one of these has to be a register, or at least one of the participants in this move has to be a register if there's a deref involved. So, like, that may not be an optimization we actually want to make. Anyway. Okay. So, I don't know that we... running this. Yeah, because I look at this and I go, yeah, that's garbage. Move from RDI to RAX, please. No one in the right mind should write this function. If we had a smarter compiler, we'd inline this function. But we're not in that situation. Okay. I think we should do run mbirdie. Okay, for this particular test, we're concerned about this change here. So I think we're just going to accept it. For this one, it was more about let's get a complicated thing and make sure this is like more of a smoke test than a problem with these particular instructions. We're not assigning anything to the stack, even in this program, this bonkers program. We're not assigning anything to the stack. If I had more time, I would have written a shorter program. Yeah, totally. Okay, so we're just going to accept those, and let's make a commit here. So in compile, we added we re-enabled patch instructions. In patch instructions, we updated it so that a program is a list of definitions. And there's these particular 2 rules they were talking about. And for the test, we updated all these tests with the new format. And then we added these 2 examples. Okay, and the snapshots. So we're going to say this is chapter... For the life of me, I can never get the UI fonts to be the correct size. This is chapter 7.10. Okay. So we are updating patch instructions pass. And let's just make sure I didn't misformat anything. Okay, we're all good. So I'm going to push. Okay. So now we're going to do prelude and conclusion. So this gets a little bit more interesting than patch instructions. Patch instructions was like, hey, let's make it fit the new program format and then do these two particular special cases, which is what patch instructions is all about. But now we have to deal with prelude and conclusion, which is all about look at what we have for the stack, make sure that we do we allocate the stack appropriately. Yeah, okay. So let's look at what it did before and let's update it. So we've got to compute the frame alignment, right? And then here's where it gets tricky. We had main, the main block. Yeah, let's have a look at this. So the format is push RVP and set RVP to the current stack pointer. So we push, we say RSP. Okay, so we move RSP into RVP. And then we align. Or no, this is the number of... Okay, we're doing it a little bit different here. We're pushing all the callee save registers that were used for register allocation. Okay, so we need to actually make sure that our allocate registers is telling us how many of those we used. Okay, so and then move, this is this sub Q16, right? Move the stack pointer RSP down to make room for regular spills. So if we allocate it on the stack, that's that stack vars thing that we have on the definition. Okay, so here it used callee, right? So this is the stuff that we need to push. And the stack vars is the int. So that's how many, and then we align it to 16 bytes. Okay, this is a little complicated. We should look at their examples. So the things that are changing. Let's get rid of those. So here, this was just about stack pointer alignment. We'll need to, when we have that set of callee save registers, we'll need to push them in a particular order and pop them back out in the conclusion in the opposite order. That's going to be important. And then we're going to have to deal with this alignment thing. And we have to also deal with the root stack pointer. And I don't know what we did. I think it didn't matter because we only had the main function in previous chapters. So we didn't do anything with R15. Yeah. Okay, so there's a little bit of problem here. This says jump to the start block. We renamed our start block. That's not good. So what I think we should do is either go back and rename the block to have start in it rather than use the name of the function. We either do that or we eliminate this jump and just find the existing block that has the same name as the function and push all of our stuff onto that. It's going to make it a little bit harder to read that. Yeah. All right. I'm going to think on that for a minute or two. And I need to take a bio break, unfortunately. So I'm going to switch off for a minute, and then we'll come back and we'll deal with deciding about what to do there. So bear with me. All right, I'm back. Thanks for bearing with me. Pro tip, don't drink a bunch of coffee at the beginning of your stream. Okay. All right, let's contextualize everything that we need to do here. Maybe what we can do without deciding about, do we reinstate the start block and break a whole bunch of things across all of our previous phases, especially the tests. Maybe the names of the blocks don't matter that much for those phases, but the tests rely on those names. Yeah. Okay. Note there's also this business where we need to initialize the garbage collector. And I think that we did that here, right? Yep. And then we move that to, right. So this is, we need this zero out root stack slots function. Right. I did that kind of strangely, but it's okay. Okay. 0-0 at halftime. Thank you, Renatius, for letting me know. I don't really have a stake in that. But I kind of wish Argentina had lost earlier. But who was going to beat them? That was the problem. Okay. So they're actually saying that this is a flattening. There's no longer an AST node for function definitions. Instead, a program is just an association list of basic blocks as an x86 level. So that was something they could have said earlier. But let's go back and read. Okay. So tail jump, we need to translate into popping the current frame. Same as the code for a conclusion of a function, except that recq is replaced with jump. So that's going to be interesting. So we already handled this. So I'm guessing up here. Right, so we generate main, generate conclusion. So that's a block. What we could do... Yeah, first of all, I think what we need to do is rather than... Yeah, okay. Let's right, so let's duplicate this file. And we're going to call this def call, not def call q, but call q. And we're going to get rid of definition. And this is just going to be blocks. And they say it's association list, right? So we're going to say it's we're going to use dictionary of string to block. And then we can get rid of definition. Yeah. And the blocks, we don't really need the live before and live after anymore. So we're just going to have a list of instructions. So I wonder if we bother with the block. And we simplify this further and say it's a list of instructions. Now we're going to have to do some translation here. Yeah, I think we're going to need to keep blocks. But what's going to go in them is... So we're using the definition before to do this this bit with alignment and are they global? Mm-hmm. Yeah, I think this is worth making a new language because we're going to get rid of the definitions. Even though that will help us format the output. By the way, my intention is to go a little bit long today if I can stand to. So we can go potentially to 4 o'clock. Before we go on, let's look at 7.12. This is an example translation. So simple function in lfun to x86. The figure includes results of explicate and select instructions. Okay. So add x and y is plus xy. And this program add 40 and 2. Okay, so there's a bit of like uniquifying things. I don't know why it did that. But you can see here this block is introducing the the add start. Okay, and then we've got the fun ref. I did that as like as Erlang syntax, like function name /2. Okay, then it tail calls with those 2 arguments, and you translate it to this, and we've got some, here we've got the definitions, and moving the arguments into the variables, and then, and then jump to the conclusion. And here, main start does the LEAQ, and the tail, it's got tail jump, right, and moving the arguments into the argument registers. Okay, and then they say global main, and main is, align the stack. What is this about? Isn't that a bug? Oh no, this is the arguments to initialize. This is saying this is set the size of the heap to this. Sorry, my bad. And then it moves that into R15 and jumps main start. Okay, so main start, move that to RCX, move 40 to RDI. Okay, and then we've got RCX into REX. This is the bit that we were talking about. Okay, and so we injected the pop RBP, so that we needed to translate this tail jump. So the big thing here is that there's no tail jump. Oops. There's no tail jump, and there's no indirect call queue. There's just call queue and jump. And we have plain jump, which is a string. So it would be like jump main start, jump conclusion. But we should have why don't we call it, for lack of a better word, indirect jump. And this is going to have as an arg. because I think that what we need to do is be able to emit this, where it's like this. The thing is, we know it's a register at this point, so we could say it's a register. And I mean, what did we do in patch instructions? We only patched tail jump, not indirect call queue. Right? So I think it still needs to be an arg. Not necessarily, I mean, I think it should be in a register probably. We may need to go back earlier in the chapter and see like what it's expecting. Yeah, let's go up there. Whoa, went too far. Okay, so it must be a register. That to me says that we need to patch instructions for call queue. Right, because if it's not, if it's in a stack location, so like we, or not call queue, but indirect call queue, right? If this is not a register, then we need to turn it into a register, which means we can just move it to RAX. And we don't have anything in our register allocation algorithm that would prefer fun refs go into registers or anything. Like there's no bias in that. It's just color all the variables. So yeah, let's deal with that. I think that that's a valid and I don't know if that's a thing that they had thought about in this book. Interesting. I don't know that we'll encounter this, but I think we need to guard against it. All right, let's go down. Yeah, it was interesting that this doesn't say anything about that. Now, it is possible. No, it's not possible. Here we just have a variable. Okay. All right. So we need to translate these. Let's go ahead and figure out what we're going to do here. I think that we need to know on the block probably just a is function. And why I'm saying that is that because we're going to be flattening this, and we'll just say false. Because we're going to be flattening this, we need to be able to mark them as the entry points to functions. This feels like a bigger transformation than I originally thought. Okay. We'll say map values. Yeah, we're going to say this is block, not list of instructions. Okay, yeah, we're going to have to deal with this. This is not correct, so let's get rid of format definition. Dict map values format block. And so map values is going to take string and block. String is the name of the block. Block is the contents. We'll say name and block. Name is a string. Block is a block. Okay, and then we don't do that. Okay, and here we're just going to say case block dot is function. And then we go global line late name. And then this is name. We've thrown away the live set, so we don't care about that. And this is block.body. Okay, we don't need format live set. Location, we're never calling that, right? Okay, we need to deal with the fact that we don't have the correct set of cases here. Just add the missing patterns. Okay, so indirect jump here is going to be this is going to have a star on it because we're going to do format arg on A. There is a problem up here. We handled, and I want to move this up here because this is tail jump. We handled that, but we didn't handle indirect call queue. So I think we need to handle that. We just eliminated it. Yeah, we need to keep this in there. Trailing commas in there. So the other thing up here that we can do is we can get I can get rid of some of these comments up here that are like irrelevant. That's interesting. We don't need that. We can get rid of var because we no longer need to deal with register allocation. And I think that this is probably a thing that maybe, I see allocate register should have gotten rid of var as well, right? But you still have definitions. I don't know that we need to add all the machinery to remove all of this. Like we could have named this def call queue to var def call queue and then removed variables here and then remove definitions here, which is what we're doing. Okay, so I think we need a bit where we're going to need some utilities to translate arguments and instructions in the generate prelude and conclusion. I haven't confirmed that, like, this is just a, I'm going to put a note in here. In the book is call queue star some register, not call queue star I don't know that this is invalid. I suspect it needs to be in a register. I mean, we can Google it. Okay, Intel, or we say x86 64 call queue indirect. Da, 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 da. Let me bump up the size so we can read that. Okay, so we're doing some of this. Yeah, okay. So register indirect jumps to the 64-bit absolute address in the REX register. Yeah, I think maybe this is valid. And I don't need to make this special case. It was not clear. So we're using the AT&T syntax, the GNU syntax. Okay, so we would be generating this or this. Let's see. There's nothing saying that it has to be REX. These examples are a little bit misleading. Right, it would probably be, if we have a deref, it's probably RDP, right? They're saying here this C code translates to this. Now we're not doing this. We're saying LEAQ, not move. It's interesting they think that this is on the stack. But we will be generating this stuff. Okay, and then there's some stuff with vtables. Ah, fun! Indirect branching instructions are susceptible to Spectre. Okay. I think we've got enough of an answer there. Okay, modern compilers feature ret pollines, which convert unsafe indirect calls into a safe sequence of call and ret instructions that isolate speculative execution. Okay. Interesting. All right. So yeah, we don't need that thing that I was doing earlier. Okay, let's make sure that we've got. Yeah, we don't need this format location. Sure, we've got everything there. Yep, indirect call queue puts the call queue star. Okay, we have no var. Thing is, map values returns a dictionary. Maybe what we should do instead is dict to list, and then we do list map. This is a pair. We call format block p.0, p.1. Yep. Okay, so we need to do the business of converting to this more limited language in addition to all of the bits that prelude and conclusion has to do. Okay. So we're going to this needs to be x86 def call queue, and we're going to EOC langs x86 call queue. And we need to change this to x86 call queue as the output. So I think what we're going to do here is similar to what we did for the other passes. We're going to just do a, like, pull this out and to handle each individual definition. So let's just make a function and stub it out. This is to take a definition. This is going to return a list of block. Or is it going to be a dictionary? Yep. And then what we'll do is we will merge all of those. Because this is, yeah, this is a dictionary of string block. So we will put a to-do in there. This is going to be input defs. And we are going to do list fold. An empty dictionary with right? And I'm going to comment these bits out because so that gives us and then we'll go x86 call queue. So this is going to be our function. We're going to move this stuff down and reconsider it. So that's our top level. And I hope that's clear enough what we're doing. We're taking all the definitions. We're going to generate their preludes and conclusions that they need. And then we will yeah, we will flatten, right? Flatten each of those blocks. Okay. So this is no longer going to take, this frame alignment is going to take the definition, right? No longer the program. The save registers is going to take the definition. We will have to, let's rename this to generate prelude. This is not main. And we need to split this out. So yeah, we may have to rewrite a lot of this. Okay, and here's the other thing. We need to take what I'm considering here is that probably what we should do, in addition to doing all of the accounting bits, we need to take our last step of processing each block as translate, right? Translate the instructions. Because there's going to be things removed that we've already talked about. Okay, you're reformatted. That's what I was running into. Here. Okay, so here's the weird bit. I think that we need to keep the generate main function, but we need to pull out the stuff that is a lit initialize happens here. We need to not call the garbage collector initialization. Except in main. Okay, so let's, how can we convey that? What I'm trying to do is like reuse as much as I can here. I am getting a little bit dizzy in this. Okay, so zero out root stack slots can stay. Generate conclusion. We'll see. We're gonna have to modify that. Whoa, why did that not collapse correctly? Okay. Multi-line header, function header. Okay. All right, so these are the callee save registers. we've got the alignment, and then, okay, so if there's no alignment change, we don't have to have the sub queue. Okay. Right, so we push RBP, we push all of the callee save registers. And then we move RSP into RBP. And then there's a question of whether we call initialize or not. And initialize is either going to call this and zero out the root stack slots, right, and I think that what I want to do here is let's not return a block here. Yeah, so we're going to rename this to generate prelude. And let's have, we'll have init GC is a bool argument. And then this is case init GC of true. We prepend that. False. False. We prepend the empty list. Not the cleanest code, but that's fine. And I want to, rather than return a block here, we're just, I don't want to go back and change everything. So what I want to do is return a list of instructions. List x86.instructions. And then we can prepend. Okay, I saved. Let's Gleam format. Okay, so what we can do is we can take this and prepend the prelude to our thing. Like it's not gonna be as pretty. I actually wish that I had not made that decision to call everything start, or remove the start and name it after the function definition, but here we are. Okay, so then let's say, okay, so compute frame alignment can be fine. Save registers is fine. And here we're going to say this is prelude, not main. Generate prelude. And here we're going to say input.name equals main, right? Or input.label. So prelude is a list of instructions. Let's see what needs to change on conclusion. Okay. So we're going to take So we're going to take the blocks that are in this. We're going to do map values. Actually, we're going to insert we want to insert the conclusion block. Conclusion name. Does this produce a block? Yes. Okay, so we've got the conclusion in there. And now we want to translate. We want to do two things. We want to translate can we not upsert? I think we're gonna have to do it in map values here. So this is block name block. Okay, and what we want to do is block name equals input.label. If it's the same, right? Then okay, I'm going to handle the false case first because this is more straightforward. We're going to say this is a block, and it's just false in the second one. And then we're going to say translate instructions. Block.instructions. Okay, so we're going to make this translate instructions function, is the gist of it. But for the case where this is the entry point of the function, we need to say, we need to prepend the prelude, right? Because we're not doing the jump from the thing to start. So we're going to map over list append prelude to block.insters and translate instructions, or translate instruction. Okay, Gleam format, please. We have a problem here. Okay, it's not instructions, it's body. That's fine. Okay, so now we need to implement this function. And this is going to be very straightforward, hopefully. So we're going to add all the missing patterns. And I want to put this down at the bottom. And we're going to have to do something that translates arguments. Because those are not going to be correct. We're going to do translate arg. Okay, and let's generate that function. Okay, so here this will be, it's nice to do this from the bottom up, but I kind of did it a bit from the top down. Okay, so this should panic. Variable was not allocated to register. Like, if we get to this point, if we didn't allocate that variable to register, we did something really bad. Okay, so that's straightforward. Variable. Okay, we can't concat. So let's just ignore. Okay, so now we can deal with all of this. This is going to be, again, the interesting ones are when we get to the other, to this stuff. So, and that's some of what we were looking at in the text of the book. Change that to pop Q. Okay, so yep, this doesn't require anything special. Nothing to translate here. This is the bit that gets interesting. We have okay, so tail jump, what do they say here? So we probably need to, rather than list map, this list needs to be list flat map. And all of these, this needs to be list of instructions, like we did in so that we can translate this tail jump into multiple instructions. Now we could potentially move that outside this and specially handle tail jump. This sequence of instructions is the same as the code for the conclusion of a function. Right, so I think that what we need to do here is... Yikes. Except that retQ is replaced with jump. Okay, so... we're generating the conclusion here. One thing I'm wondering is, do we need to generate that? Do we need to insert that conclusion block? Does this even need a block? If we have a tail jump in our function, we don't ever need the conclusion block because it's unreachable. I don't want to over optimize this, but I'm wondering here if like I can say well, regardless, I think that this needs to be, we need a conclusion thing here, which is, we need to be able to handle this tail jump. Okay, so one thing that we can do potentially is just say that this is the contents of the conclusion. Yeah. And let's not. Let's not inject this conclusion. I think what I want to do here is change this to, rather than return a block, return a list of x86 instructions. And then we don't have to construct the block, we just return this. And the other thing is, don't inject the retQ. And I think, I'm not sure if there's a possibility of a branch and then a, yeah, I guess there would be. You either jump to the conclusion or you tail jump. That's a very common possibility. So let's not put the ret queue in there. And then what we'll do up here is we're going to say conclusion. Let's put the concluding thing in there. And then we'll do another pass that finds any direct jumps to the conclusion name. And if there are any in the blocks, then we inject the conclusion as a block. So I'm going to be dumb and call this maybe inject conclusion block. And we'll take the conclusion and the conclusion name. And this is going to be to do doesn't like formatting my file if I have things that are broken. Okay, so here it's going to be like conclusion, or we, yeah, is dict. Is there any? Let's see what the standard library does. No, not that. Standard lib. There's no find. We do fold. This is, let's rename this to blocks. We're going to fold with false. And then we don't care about what the name is. This is the block. So any that's getting ugly. Okay, so we want to say if it's jump, what's wrong here? Okay, so dict fold. Oh, right. This takes the accumulator, and what we want to do is OR the accumulator. Whew! I kind of want to extract this into a function. Wrong. Okay, let has jump equal this, and then has jump. And then let's extract that into a function. Okay, and we're gonna rename that to has jump to conclusion. And yeah, I need to deal with this. And let's inline that variable. Okay, so I wanted to name this because we need to. It's better to have a name for this, and like we don't need the conclusion if there's only tail jumps in this definition. Yeah. Okay. Here's the thing. This should we should probably do this. I'm getting dizzy here, folks. It's 4 o'clock, but okay, this bit we should probably do in the outer scope. So let's say this is x86 call queue instructions, and then out here in generate player and conclusion. Okay, so we're gonna do this, and we're gonna pipe it to list map. With the empty list there. Sorry, flat map. And this, the translate instruction, this needs to be x86 call queue. That way what we can do here is go this tail jump is append, so put the conclusion on the front of, this is what the whole point we went through, to a jump, right? And translate arg of the label. Or indirect jump, right? Okay, that was the whole thing. All of this business we did. Such a pain. Okay, so let's go ahead and do the rest of these. This is going to be retq. Here we're going to do aq, translate arg, translate rb. I'm sorry, all of these are lists, and we don't care about the arity. We're throwing that away in both cases. And actually, this indirect call queue in here, we should throw away the arity as well. Don't care about it. And we don't care about it with call queue. Isn't that fun? We don't need to track that. We have handled it. It's kind of nice to have the, you know, the annotation there, but it's not strictly necessary for this. So okay, that was a lot. And here I am just like mechanically changing things again. But the essence of it here is that it's what they're trying to say here. Like the tail jump is not just simply jump, like an indirect jump to whatever the argument is. It need to pop the current frame, right? So like all the things you would do in the conclusion, except you replace retq with jump. So that's what we're doing here. We're saying we're pre-generating the conclusion, and then we only add that block if we need it. Otherwise, we do tail jump, right? So, all right. I think where I want to end this stream is let's finish these mechanical translations like we've been doing. Make sure that it at least compiles. And then we'll wrap up testing of this next week. And I think that I'm sorry, I'm just doing some copy pasta here. I think the compiler or the LSP is not keeping up, which is okay. And then we'll update the prelude and conclusion stuff with the new things that we need to handle next week. Okay, so those two are fine. This needs to translate arg. just going to replace these. Especially these AB ones are really easy. Okay. All right, so let's quickly write some to-dos in this file so I don't forget. I want to look at the instructions here. All right, so oh, that's why we have problems over in call queue. We no longer have the arity on call queue. That's fine. We don't have the arity on indirect call queue. Also fine. Okay, let's see what's wrong down here. All right, so this is already known to be a byte register, so we don't need to translate it. And this is already known to be a byte register, so no translation call necessary. We throw out arity. Okay. No failures, so all right, quick to-dos. So let me hide the project tree again. Okay, so we in the prelude push RBP, move to RSP. We already have that done. Make a little to-do list here. Okay. Push callee save registers. We already do that. We did that last time. Align. So move RSP down for alignment. We already do that. And when I put these comments down here, by generate prelude, right? Okay. So push RBP and all the callee save registers. We align RSP. Okay, so we need to move root stack pointer R15 up by the size of the root stack frame for this function. That's this root stack slots. Main does init GC initialization before step 4, before moving R15. Okay, so that needs to happen. Then we need to move the root stack pointer up. So yeah, so we need to do that. We need to do the initialization. Okay, so we'll need to refactor this a bit. And then the last bit is jump to the start block. And I'm going to say, I'm going to put a dash in here, not doing, just prepending the prelude. I mean, there are probably good reasons to make the prelude separate, but maybe we'll do a refactor later. Right. Okay. So the conclusion has to do things in reverse order. So move the stack pointer back up past the regular spills. Restore Kali saved registers by popping. We're going to see if these are already done. Move the root stack pointer back down by the size of the frame. Restore RBP by popping. And then return with retq. And I'm going to say not doing happens outside this function, depending on whether the function only tail calls. Okay, so let's see. Right, so we are so the root stack pop, it looks like we already do. That's just changing the pointer. So we already do that. It doesn't say what order we should do this in, so I'm assuming it doesn't actually matter that much. But we get the alignment, and then we pop. Yeah, so we do it actually kind of, we pop the registers. Okay, we do the root stacks. We're kind of manually doing this in reverse order. And so we're doing it like root stack first, and then the alignment, and then restore the Kali save registers, right, and RBP. Okay, so I think that we're done on conclusion. We already handled this R15 thing in the root stack pointer in the last chapter. So we don't need to do anything with that. We do need to make sure that we need to make sure that we get this this bit. because we didn't before. We just... Oh, wait. No, it's right here. We're doing that adjustment here. So I think actually we got this, right? I think we can do some cleanup here, but we'll wanna verify that this is correct next time. So thank you all for hanging out for so long. I can't believe I did such a long stream today. But I will see you next week. Thanks for hanging out.